One question we get asked a lot is how the DAT expects you to do a lot of the math in the general chemistry section without a calculator, especially math problems that involve calculating logarithms in your head, like things with pH or POH. This video is intended to teach you how to calculate logarithms in your head. Let's start by reviewing what a logarithm actually is. When we write log, we typically are talking about a log base 10. And what a log base 10 means is 10 to some power equals 10. So if we write the log base 10 of 100, again, what we are saying is 10 to what power equals 100? Well, we know that 10 to the second power equals 100. I just wanted to review that because all of the logs in the general chemistry section, all the logs you'll be asked about there, are base 10 logarithms, meaning that they're asking you 10 to what power equals this value here. Now the logs on the DAT are not typically this simple, and they're usually written in scientific notation. So you're usually given something like this. We'll realize again here that we're talking about a base 10 logarithm. So we're saying 10 to what power equals 1 times 10 to the 2. Realize that 1 times 10 to the 2 is the same thing as just saying 10 to the 2. 10 to the x equals 10 to the 2, we can clearly see that x equals 2 if we want those two sides to be equal. And this holds true for any scientific notation that is 1 times 10 to the something. So 1 times 10 to the x is always equal to x. The log of 1 times 10 to the x is always equal to x. So if you had the log of 1 times 10 to the 8th, that would be equal to 8. Again, because what we're saying with the log is 10 to what value, 10 to what power is equal to 10 to the 8th. Well, 10 to the 8th is equal to 10 to the 8th. Now let's say that we had the log of 1 times 10 to the 8th, and we know that equals 8. And we're also looking at the log of 1 times 10 to the 9th, and we know that that equals 9. And I ask you, the log of what value equals 8.5? So which value is halfway between these two logs, 8 and 9? The answer is the log of 3.16 times 10 to the 8th gives the value of 8.5. Now why is this 3.16 instead of 5? Because 5 times 10 to the 8th would be halfway between 1 times 10 to the 8th and 1 times 10 to the 9th. The reason it's 3.16 instead of 5 is because this is a log scale, so it operates differently than just a linear scale. You don't really need to worry too much about that, but you should memorize this value. 3.16 is the magic halfway point of logarithms. Now the reason this is useful is because if I asked you to calculate something like the log of 7 times 10 to the 8th in your head, that would be very difficult to do. But understanding this halfway point can help us find the answer to this question. The way we're going to approach these types of questions is we're going to say, well, if it was the log of 1 times 10 to the 8th, that's easy. We know that's 8. If it was the log of 1 times 10 to the 9th, again, that's easy. We know that's 9. And now we know that if it was the log of 3.16 times 10 to the 8th, that would be 8.5. Now all we have to do is find where our value here fits in to this scale. We start in this place. We say 7 is larger than 1, so we know our log will be larger than 8. 7 is also larger than 3.16, so we know our log will be larger than 8.5. However, 10 to the 8th is smaller than 10 to the 9th, so we know our log will be smaller than 9. So we can narrow it down to this range and say we know our log will be between, we know our answer will be between 8.5 and 9. That's useful because the DAT would give you answer choices like 6.3, 7.9, 12.3, 8.8, and 10.6. Notice that only one of these answer choices, 8.8, falls within our desired range. The DAT is not going to give you multiple answer choices within a 0.5 range of one another. So if we can narrow it down to this 0.5 range using 3.16, the halfway mark, we'll be able to get these questions right and do the logs in our head, saving us time on the chemistry section. Now you may be saying to yourself, these logs are a lot easier than the ones we see on the DAT, and that's true. Let's go over some harder ones and see how they may actually show up on the DAT. When we're working with pH and POH, the values are usually so small that they have negative exponents rather than positive exponents. However, we learned clear back over here that the log of 1 times 10 to the anything is equal to that anything. It's just equal to the power on that 10. The same still applies here. The log of 1 times 10 to the negative 6 is just negative 6, and that holds true again for any negative exponent. What about the log of 1 times 10 to the negative 5th? Again, that's just negative 5. The difficult part about working with negative logs is remembering and realizing that 1 times 10 to the negative 5 is a larger number than 1 times 10 to the negative 6. The smaller the negative exponent, the larger the number. That's the difficult part. It's backwards from the positives. So again, I ask which log would give us the halfway point. That would be the log of 3.16 times 10 to the negative 6th. We're doing the same thing. Here we take 3.16 and multiply it by the smaller exponent. Negative 6 is smaller than negative 5, so it's 3.16 times the smaller exponent gives us our halfway point. That was true of the positive exponents as well. 3.16 times 10 to the smaller exponent, 8 is smaller than 9, gives us the halfway point between 8 and 9. So the hard part is remembering that negative 6 is in fact smaller than negative 5. So let's say on the DAT you had a problem where you were trying to find the log of 2.7 times 10 to the negative 8th. We're going to solve this really similarly to how we solved the log with the positive exponent. Let's make it easier on ourselves. Let's say, what if this was the log of 1 times 10 to the negative 8? We know that's negative 8. What if it was the log of, and remember we have to pick the bigger power here. The larger power is negative 7. The log of 1 times 10 to the negative 7 is negative 7. That's also easy. Our halfway point, log of 3.16 times 10 to the smaller of the two exponents, negative 8, is equal to negative 7.5. So now we just need to find where our log fits into this scale. 2.7 is larger than 1, so we know our answer will be larger than negative 8. 2.7 is smaller than 3.16, so our answer should be smaller than 7.5. In other words, our log will be between negative 8 and negative 7.5. You may be thinking, this seems to take a long time. I don't have time on the DAT to write out all three of these and find where my specific log fits into the scale. That's true, it does take a little while, but if you practice this a couple times, you'll get really quick at it. You'll get to the point where you can look at this and say, rather than drawing out this entire scale, you'll just say, well, 2.7 is larger than 1, but smaller than 3.16, so it's going to be between negative 8 and negative 7.5. You'll be able to do them really quick, but it does take practice. Let's do one last example and recognize that there is one more wrinkle the DAT throws in, and that's the fact that we're doing negative logs of negative exponents because pH is a negative log. The P in pH stands for negative log. That's why when we see pH, we say that's equal to the negative log of the H plus concentration because P stands for negative log. So for our example problem, let's calculate the pH of a solution with H plus concentration equal to 5.26 times 10 to the negative 5th. We remember first that pH is equal to the negative log of the H plus concentration. So if we're trying to find the pH, all we need to do is take the negative log of the H plus concentration, which in this case is 5.26 times 10 to the negative 5th. We go through the same steps we have before by saying, what if it was the negative log of 1 times 10 to the negative 5th? That would be equal to 5. Notice it's no longer negative 5 as it was in previous examples because we're now multiplying the final result by a negative 1. So if we just took the log of 1 times 10 to the negative 5th, it would be negative 5. But we're taking the negative log of 1 times 10 to the negative 5th, giving us 5. We also say, what if it was the negative log of 1 times 10 to the larger power, negative 4? Well, that would give us 4. Lastly, we write our halfway point formula. If it was the negative log of 3.16 times 10 to the smaller power, negative 5, we would get 4.5. Now we just need to find where our log fits into this scale. 5.26 is larger than 1, so we know we need to keep going down the scale. 5.26 is also larger than 3.16. However, 10 to the negative 5th is smaller than 10 to the negative 4th, so we know our answer will be no bigger than 4. Thus we can say our answer is between 4 and 4.5. Thus we can say the pH of our final solution is between 4 and 4.5. Now if you were to punch into your calculator negative log of 5.26 times 10 to the negative 5th, you would get out 4.28 or 4.3, which is right in the range where we predicted it would be and would be the correct answer you'd select on the DAT.